When looking at a wave, there are a few characteristics that we can describe. First, let's talk about the amplitude of the wave. This is the maximum displacement from equilibrium. So if this is our equilibrium, our zero line, the amplitude would be the length or distance from that equilibrium line to the very highest point. Or likewise, it would be the distance from the equilibrium line to its lowest point, because the distance to the highest point from equilibrium would be the same as the distance from equilibrium to its lowest point. The next feature that we can talk about is the crest. Sometimes we'll refer to this as the peak as well. The crest is the highest point above the equilibrium position. So the highest point, we refer to the crest, like the crest of a wave. The lowest point from the equilibrium position we refer to as the trough. So we can talk about the highest point, crest, and the lowest point, the trough. The wavelength, which is represented by the Greek letter lambda, is the distance between two adjacent similar points of the wave. In other words, it could be the distance from crest to crest, or it can be the distance from trough to trough if there is the continuation over here, or it could be the distance from equilibrium position when it's going up to consecutive equilibrium position when it's going up. So wavelength, for the easiest purposes, we can say is just from crest to crest. Those are the most visible of all locations. And that wavelength is going to be measured in meters. When talking about different types of waves, there's of course light waves, there's also sound waves. A light wave, when we talk about visible light, we have violet light, and violet light has a wavelength of 400 nanometers. So the distance from crest to crest of violet light is 400 nanometers, where a nanometer is a billionth of a meter. So very small wavelengths. Red light has a wavelength of about 700 nanometers. So red light has a longer wavelength, which corresponds to a different color. So based on the wavelength of light, we get different colors. There's two types of waves that we want to talk about. The first type of wave is a transverse wave. This would be like light. Light is a transverse wave. This is a wave whose particles vibrate perpendicular to the direction of the wave motion, or its propagation, as we like to say. So if the wave is moving to the right, the particles, or in the case of light, it would be an electromagnetic field, the particles, or electromagnetic field, would be moving perpendicular to the direction of the motion. So think about a slinky, where you move the slinky up and down, or a rope where you move it up and down. Although the wave travels forward, the actual rope is moving up and down. And so we refer to that as a transverse wave. There's also longitudinal waves. Sound is a longitudinal wave. This is a wave whose particles vibrate parallel to the direction of the motion. So in this case, the particles are moving left and right, and the wave is also moving to the right. So think about that slinky again. If I pull back on the slinky and let it go, the slinky moves back and forward as it vibrates. And at certain points, the slinky itself is compressed. So we call that a compression. At other points, the slinky is stretched, and we call that a rarefaction. And so when we talk about the wavelength of a longitudinal wave, what we're really referring to is the length from compression to compression, or likewise from rarefaction to rarefaction. Okay, so it's the same type of situation. But sound is a longitudinal wave in that the air molecules are vibrating back and forth parallel to the direction of the motion. Next thing we want to talk about is something called simple harmonic motion. This is when the vibration about an equilibrium position in which a restoring force is proportional to the displacement from that equilibrium. In other words, the amount of force that is applied is proportional to how far it is being stretched or moved. So an example of this would be a pendulum. The further I pull the pendulum to the side, the larger the restoring force. The larger force there is to bring it back to its bottommost position. Same thing with the mass on a spring. The further I stretch the spring, the more force there is exerted by the spring to pull it back up. When talking about simple harmonic motion, there's two things that we're going to discuss, and that first thing is the period, and this is the time it takes to execute one complete cycle of motion. In other words, it's the time it takes for a pendulum to move back and forth in one cycle. So it is the amount of seconds it takes to move over and back. For a spring, it would be the amount of time it takes to move up and back down. So the period is the time it takes, measured in seconds, to go through one complete cycle. The abbreviation of period, the symbol, is the letter T because it's measuring a time. We can also talk about the frequency, which is the number of cycles or vibrations per unit of time that occur. This is measured in hertz, which is an abbreviation of a cycle per second, or 1/seconds. So if I talk about that pendulum, it would be how many times does it go back and forth in 1 second. If I talk about the spring, it's how many times does it go up and down in 1 second. That's the frequency. So the relationship between the frequency and the period, frequency, by the way, is a lowercase letter f. The relationship between the frequency and the period is that they are inversely related. So frequency is 1 over the period, or likewise the period is 1 over the frequency.